Hey guys, welcome to another video of quantum field theory. In today's video, we'll be going over the Fock space, which is the main state space that we work in quantum field theory. So let's begin. So in quantum mechanics, we're going back to quantum mechanics, we have something called the state vector, right? And the state vector encodes probabilities of finding certain things about our system. The state vector is a pretty abstract object, so we like to project it on to what is called the position basis vector. And by projecting the position basis onto our state vector, we get the wave function, which is much nicer to work with since it gives us a pretty geometrical picture that tells us like where we are more likely to find a particle, or where we are more, or what momentum the particle is likely to have when measured, and other sorts of cool questions. So that's for one particle quantum mechanics. But we can also do quantum mechanics for two particles. So again, we still can describe the system of two particles with one state vector that remains constant. And we can describe our system as being the state vector, which is equal to what's called the tensor product of the state vector for one particle and the state vector for another particle. Now this symbol over here, this is called the tensor product. And the tensor product can be thought of as a way to build matrices by sort of composing vectors together. For example, say we have some vector 1, 2, and some vector 3, 4. The tensor product of 1, 2, and 3, 4, the vectors v and w, is going to be 1 times 3 for the first entry, 1 times 4 for the next entry, and then 2 times 3 and 2 times 4. So our tensor product is 3, 4, 6, and 8. So the tensor product allows us to build more complex matrices from smaller matrices, basically. And that's what we are doing here. We are saying that the states vector for a two-particle system is a tensor product for the state vector of one particle and the state vector for another particle. So we can use a bit of simplifying notation. We can write the state vector as psi1 and psi2, where we define putting psi1 and psi2 together. We define that as just being the tensor product. So it's a shorter way to just write it out like this. So again, this represents the state vector for having, let's use red, for particle A being in the state psi1, and then particle B being in the state psi2. And we can project this state onto the position basis, and we get psi of x1 and x2, where psi of x1 and x2 equals psi of x1 times psi of x2. So if the former vector picture didn't make sense, here is another way of thinking of the state state vector for multiple particles. So now our wave function will have like an x1 axis and an x2 axis, and our wave function becomes like three-dimensional for just two particles, and it exists in what is called a configuration space. So that's pretty simple so far. We can generalize this to three particles. We can have psi of x1, x2, and x3. You get that by just multiplying psi of x1 times psi of x2 times psi of x3, and so on. Now, for the case where we have the state vector, it's just the tensor product of psi1 and psi2, We call this a separable state. And we call it that because we can simply separate it into just one for psi 1, or we can separate it, for like one for psi 1 and one for psi 2. So we can just take our state vector and we can just simply separate it into like psi 1, tensor product psi 2, tensor product psi 3, and so on. We can straightforwardly separate our state vector. Also, another cool part about these states is that the state psi 1, tensor product psi 2, is not necessarily equal to psi 2, psi 1. Because the tensor product for the general case is not commutative. So psi 1 tensor product psi 2 is not going to be equal to psi 2 tensor product psi 1. So again, the first entry represents what we call particle A. The second one is going to be particle B. So this state just represents, to put it in words, it represents that particle A is, or particle A, yeah, I think that is in states psi 1. And this, yeah, so, and then particle B is in state psi 2. This means, again, we still have this first entry being A, and the second entry is going to be B. This means that particle A is in state psi 2, and then particle B is in state psi 1. So psi 1 and psi 2 aren't attached to A and B. A can be in psi 1, and A can also be in psi 2. So psi 1 doesn't mean first particle. Psi 2 doesn't mean second particle. Psi 1 is just some state. Psi 2 is another state. And then a particle can have either one of those states. Now, this just means that if we have a particle A in state psi 1 and particle B in state psi 2, if we swap those particles, if we swap their states together, there is an actual difference in the state vector. So you can tell if the particles swap their state. So we call these particles distinguishable particles, because if we exchange psi 1 for psi 2, well, then we can actually notice a difference. The state vector will change, meaning that the probabilities that result will also change. An important thing to note here is that this state, psi 1, psi 2, exists in the Hilbert space, but for two particles. So before we just had like psi 1, which is a member of the Hilbert space for one particle, but this state is now a member of the Hilbert space for two particles. And the Hilbert space is just a state space that these particles live in, right? We can have a one particle Hilbert space. We can have a two particle Hilbert space. And the Hilbert space is, again, it's a space where these vectors live in, or the more mathematical precise definition is a vector space that has some inner product on the space, which we do have for these state vectors. And yeah, so we can say that the Hilbert space for two particles is just the tensor product of the Hilbert space of one particle system. Since remember that psi 1 is a member of H1, psi 2 is also a member of H1. It's also a one particle state. And then psi 1 tensor product psi 2 will exist in the Hilbert space H1 tensor product H2. Or, sorry, not H1 tensor product H2, H1 tensor product H1, which we will call H2. So that's some important formal stuff that we have to get in the way. And yeah, so what we've discussed here shouldn't actually be new. This is just a review of quantum mechanics, but it's important to mention that for what comes after. So we can also consider particles. We can also consider states that look like this. Now these states are very different from these ones. This is a separable state. We can write it in just psi 1 and psi 2 when we're done. But this state that we formed here, it's not separable. We have to like, we've sort of repeated ourselves ish. If it just stopped here, we would have a separable state. But since we add another state, it's no longer separable. We don't just have psi 1 and psi 2. We have psi 1 and psi 2 plus psi 2 and psi 1. So we call this state not separable. Another word for that is entangled. If you ever heard of quantum entanglement, this is what it means. This is an entangled state. Entangled states, they're a whole basket of fries on their own because they have all these cool implications, but we won't dive into those for this video. The main takeaway here is that for entangled states, our vector is a bit peculiar because for this particular entangled state, called a bosonic state, we don't really have a clear concept of like particle A and particle B anymore. Like if you were to label this A and this B and this A and this B, well, now we have that particle A is in state psi 1 and psi 2, which makes no sense. So we don't really have a sort of defined like sense of, or at least the mathematics doesn't clearly tell us about particle A and particle B. It just tells us they have the probability that we measure this state, and we have some probability that we measure this state. That's really all the math tells us in the Copenhagen interpretation, of course. Now, the weird thing about this state is that if we, how do I word this? Like, say we measure this state, like we measure like this system of particles, and we find out that the particles are in this state over here. So this means that particle A is in state psi 1, and then B is in state psi 2, right? Then, if we were to measure it in this state, psi 2, psi 1, in some like alternate reality, this would mean that particle A is in state psi 2, and then particle B is in state psi 1. Now, say that we measure them and we get the first result. So say we get the first result, and then we stop measuring and we allow the state to go back into a superposition of these states, and then we measure the system again, and we get the second result. So here's result number 2. Here's result number 1. So we first measure the system, we get this state. We measure it again, and then we get this state. So, what you guys might think is that, oh, particle A took the state of particle B. Like, particle A was in psi 1, particle B is in psi 2, and now particle A, like, sort of changed the, like, it just swapped places with particle B. But it turns out that you actually can't tell if that happened. You can't tell if particle A, like, changed its state or to particles B state and vice versa. We can't really tell that because if we were to change psi 1 to psi 2, this state remains the same since we're just adding them together. Here's a better way of showing it. So we have that psi is just psi 1, psi 2 plus psi 2, psi 1. If you were to exchange psi 1 with psi 2 and psi 2 with psi 1, we get that psi is psi 2, psi 1 plus psi 1, psi 2, which is the exact same state. So the basic idea here is that if like if particle A, let's just use position here as a good example. If particle A took on the position of B, like if they just changed locations together, our wave function would actually still be the same thing. Like, so we won't be able to tell if they did change their position because our state vector is the same. Now we could measure them as having different positions, but we won't be able to actually tell if they changed positions, right? So we can say, oh, particle A is in position 1, particle B is in 2, but like after, if we were to measure it again, we can't know if like A changed positions to B and B changed to A. We can't tell that. We can't tell the difference because their state is symmetrical. So we call these weird particles, these weird entangled particles, we call them identical particles for this reason. And these were bosonic identical particles. Particles described by the state, they're called bosons. And we can also build another state that's where we have psi 1, psi 2, minus psi 2, psi 1. Psi 2, psi 1. And if we were to change the states, if we change psi 1 for psi 2 and psi 2 for psi 1, we'd have some new state, let's just call it this thing prime, equals psi 2, psi 1 minus psi 1, psi 2. You guys might say, oh, our state changed, right? And for these kind of particles, we call them fermions. Sound familiar to you guys? Fermions? So we call these particles fermions are described by this state vector. So this is also an entangled state. Now you guys might say that these particles are going to be distinguishable, as in, which means not identical, because our state vector does actually change when we change psi 1 for psi 2, but it only changes by a phase. It's like, because psi prime is equal to negative psi. And this negative is a phase. It's going to be a phase where our angle for the phase is going to be pi. So since the state is different only by a phase, the resulting probabilities are going to be the same. So even though the state did change, we still can't know that it changed because the probabilities for certain things will stay the same. So this is actually still going to be a state that describes identical particles. Even though the state will change, the probability of density won't change. So these particles are also identical particles. And for these fermions, say we had two fermions in the same state, right? We would write that as this, psi 1 minus psi 1, psi 1. So you have two fermions that are both in like location 1 or in energy 1 or in momentum P1 or whatever. Well, that's just going to be 0. So this tells us that we can't have two fermions in the same state. Or in other words, psi 1, psi 2 equals negative psi 2, psi 1. And we call this anti-symmetry. There's a very deep reason why fermions are anti-symmetric that we'll be exploring more in quantum field theory. So that's all we've done here was just quantum mechanics. So this should have all been review. So for quantum field theory, we are going to build off on all of this. So for quantum field theory, we can actually have particle states that have a different number of particles. So in quantum mechanics, right, we could have like H3, which is the tensor product of just one particle states that have a 3 particle state, right? And then we could have H2, which is the tensor product of just one particle states. But what if we had the state psi 1 plus psi 1, psi 2? This is a very strange state because the state contains a basis that have a different number of particles. Different number of particles. In quantum mechanics, we don't see the state because the number of particles is always conserved in quantum mechanics. But in quantum field theory, we can actually see a state that looks like this, where we have one particle for one. It's a combination of one particle states and a two particle state. And this state is really weird because what if someone asks you, hey, how many particles are in this state? Well, we can't really easily answer that question since the state is a combination of particle states that have a different number of particles. So we can now have the number of particles no longer be conserved in quantum field theory because of states that people say that they don't have a well-defined number of particles, which really means that the state isn't an eigenvalue of what's called a number operator, which we will be seeing in the future. So a better way to write this state would be like A psi 1 plus B psi 1 psi 2, where A squared is the probability that we measure the system as just psi 1, and then B squared is the probability that we measure the system as psi 1 and psi 2. So we have a probability that we measure one particle, and we have a different probability that we measure two particles. So that's a really cool thing to have. We can have a states vector, because before our state vectors, right, the basis always had the same number of particles. Here's 2 and here's 2. But now we can have 1 and 2. We can go even further. We can have 1, we can have 2, we can even have 3, and so on up to infinity. We can have a basis that have all different kinds of numbers of particles. We can have a state that has 1 billion particles plus a state that has 1 particle, even a state that has 0 particles, the vacuum state. So the number of particles, we can superimpose those to get a state that doesn't have a clear number of particles. All we can say in the Copenhagen interpretation are the probabilities of obtaining a certain number of particles. So that's what happened in quantum field theory. We can have states that don't have a clear number of particles. So basically, we can sort of add the 1 particle Hilbert space with the 2 particle Hilbert space, with the 3 particle Hilbert space, and so on. We can add these different spaces together to get a whole new kind of space, where we call that a Fock space. And that's what the Fock space is. The Fock space in quantum field theory is sort of like the Hilbert space 2.0, because the Fock space is technically speaking a Hilbert space because it's an inner product space, but the Fock space is a more bigger, it's a larger space, because not only do we have 1 particle states, 2 particle states, 3 particle states, but we also have states that are a mixture of those 1 particle, 2 particle, and 3 particle states. So the Fock space, we call that F. We can have like psi 1, we can have psi 1, psi 2, we can have psi 1, psi 2, psi 3, we could have psi 1 plus psi 1, psi 2, we can have psi 1 plus psi 3, and we can have a bunch, like any combination that we want, we can have that. So our Fock space allows us to add states that have a different number of particles. And the mathematical way to write out the Fock space looks like this. So here's how you'd actually see the Fock space being written by a mathematician. Physicists don't really write it like this very much because, well, very abstract. Technically speaking, we should have some line on top of here, where this line is called the completion of this Hilbert space. Completion is a term that's used in topology. we don't really have to care much about that term right now. But here is how you would actually write out the Fock space. So the Fock space would just be the tensor product of the Hilbert spaces, which is just one particle state, two particle states, three particle states, then states that are also being added together that have different particle numbers. That's what this means over here. We have this nu over here. Now, when nu is positive, we have bosons. The state describes bosons. When nu is negative, we have fermions. So this this S nu over here, I believe it's called the symmetry operator. If we have, let me just erase what's below here for more room. If we have S plus, that just means that we are dealing with states that are antisymmetric. So like psi 1, psi 2 equals negative psi 2, psi 1. Sorry, that's for S minus. Not S plus, S minus. So S minus means that we are describing bosonic particles. For S plus, that means that our states are symmetrical, where psi 1, psi 2 equals psi 2, psi 1. So these are, these aren't bosons, these are fermions. Sorry. And then these are bosons. So that's what this S operator means. It's just telling us whether we are using bosons or fermions. And this symbol over here just tells us that we are like also adding the Hilbert spaces together, and then we are taking the tensor product of Hilbert spaces. So you can think of this Fock space as being like H1, tensor product H1, then like plus H1, tensor product H1, tensor product H1, and so on. So we worked with the Fock space in quantum field theory because we want to describe states that have a basis which contains a different number of particles. So we can just describe things like decays. We can have one particle that splits up into two particles, right? We can't have that in quantum mechanics, but in quantum field theory, we can have that when we are working with the Fock space, where we have states that can be written as a one particle state plus a two particle state. So that's pretty much it for this video, and that's how the Fock space works. In the next video, in quantum field theory quantum field theory 2, we will be, actually I don't know what we will be doing. I'll figure that out. See you guys later, and I hope you guys enjoyed this video. Bye.